Make sure you have your mole notes before we start the fun. Today's review is going to be, again, just that. You should recognize these skills. The only little twist that I have waiting for you is at the very end, there's one thing that's a little different than what you did last year. So stay tuned for that. Anyway, before we dive directly into the mole concept, though, I want to revisit average atomic mass. But let's remember real quick where the numbers come from. So, you don't need to get yours out, but if you look up there, you look at the periodic table, you'll notice that the masses, of course, are mostly decimal numbers. So if you look at hydrogen, then you'll notice that it's 1.008. And here's what they're doing, in case you forgot. It's an average of the different hydrogens, the different species, the different isotopes that exist. In nature, we have found hydrogen 1, hydrogen 2, and hydrogen 3. Those are three different isotopes of hydrogen. That's all an isotope is when something exists in different masses. And those are three different masses. 99% of hydrogens, though, have a mass of 1, which is almost all of them, right? It's the other 1% that are either H2 or H3. So what scientists did is a weighted average to show you the average atomic mass while remembering that almost every single one, 99%, has a mass of 1. So when you look at the number, 1.008, it almost completely ignores the existence of H2 and H3 because they're almost all H1. It's a little bit above H1, the average is, to account for their existence. But the weighted average really makes it pinpoint the number 1. The way that they come up with this is that red equation. So I want to remind you how to use the red equation. And then there's a more annoying way that they can ask, which is the green equation. So let's just dive in. All right, so we'll do the easier one first. Using that red equation once again. What you'll notice is the oxygen isotopes there. 3 of them, right? O15, O16, O17. Hey, which of those oxygens is the most common? 16, right? 83% of the oxygens have a mass of 16. That's important to know. But let's see if we can use that data to get an average atomic mass, a decimal number similar to the ones on the periodic table. Plug and chug. To find average atomic mass, you're going to take the first isotope, which is 15, and multiply it by its percent abundance. But, like you wrote on the previous screen, it has to be the decimal version. How do you turn a percentage into a decimal? Divide by 100 is the answer. What they said was slide the decimal to the left twice. It's the same thing. So what I'll get there then is 0.161. And then if you follow the equation, plus the next data set. The next oxygen has a mass of 16 times its percentage as a decimal divided by 100, and you'll get 0.83. The equation has an ellipses because there could be a bunch of isotopes, like tungsten has 5 different isotopes, so there'd be 5 data sets. Oxygen has 3, the other one being oxygen 17 at 0.009 if you turn it into a decimal. See if you can get to an answer on your calculator. Type it in exactly like that. I get an average atomic mass of 15.85 AMU. This skill does not apply sig fig. So really the anytime you're getting a mass like this, you always go 2 digits past the decimal. But even if you do it wrong on an FRQ, College Board won't take points away for this type of skill. So I'm not going to stress over it. AMU is the units for average atomic mass. But again, they won't ask you for those. You're like, it's not a big deal if you can't remember. Are we all right there? Hey, what whole number does this round to? 16. Remember what the most common isotope of oxygen was? 16. So that's what happens, though, right? The weighted average makes the number gravitate towards the most common of the species. The other equation's more annoying. What if it's the percentages that are missing? So if you look at this new question, all right, you'll notice that we don't have any percentages given, so we've got this green equation. The red and green equation will be given to you, so you don't have to worry about memorizing those. But the algebra is a little bit more involved here. So focus in. Let's see who can do math. See how there's decimal versions? That's called mass defect. You're not going to have to defend what mass defect is. I'll tell you what it is. It's the idea that protons and neutrons don't have a mass of exactly 1. And so when you add them up, it doesn't equal real whole numbers. I just show this as an example because if they give you a mass defect number, a more precise value, you have to use that value. So let's use the parentheses value. Here we go. Isotope 1 is 120.904. Times X. Following the green, plus isotope 2, listed at 122.903, times 1 minus X. Now, this equation, since we're looking for the percentages, forces you to go and fetch the average atomic mass of the element from the table. The one that I grabbed when I first wrote this down was 121.76. I think it's been changed to 121.75 since then because they redo the data every year based on isotopes information in research. We're going to get the same answer, but let's use this number even if your periodic table is 100th different. Bless you. Now, if you can solve for x, you can do the problem. The question is, can you solve for x without me? I bet you can. But let's start to simplify. Here we go. This times this is going to be the same number x. But here we have a distribution, right? Distributive property. First, this value times 1. All right? All right, so there's the plus. And then that value times 1 is itself. But then distribute it to the x. Look at that minus sign. All right, so it grabs onto that x. Bring down my value. We all right? What's the name of the next step? Second and third period both had it. Combining like terms. Very good. Yeah, so I've got a couple items that have a variable and a couple items that don't. So let's combine the variable items first. Now look, the x containing expressions are on the same side of the equality, which means we're just going to do what it says. We're just going to take this minus that. I'm going to show it over here, though. So I'm just going to bring this over. This minus this. All right, which essentially, it essentially gets rid of that, right? And you'll get a difference there of negative 1.999. Combine the other like term, which is the non-variable, but notice that these two dudes are on opposite sides of the equality, so you have to do the opposite function, right? This is adding, but I want to get rid of it from the left, so I'm going to subtract it, which again will essentially remove it from over there. And what we do from one side, you do the same to the other. So what it says right now is this x expression, if I bring down this equality, equals that. All the other numbers have been moved or canceled or whatever. So it's this equals that. And now we can isolate the x by doing what? Yep, dividing. It's multiplying right now. So if we divide by negative 1.999 on both sides, of course, it'll isolate the x. And once x is isolated, I will be very close to an answer. That is the abundance of the first isotope, but it's not a percentage. How can I turn it back into a percentage? Times 100. Slide the decimal to the right twice, whatever. You're going to get 57% for the first isotope. So what must be the percent of the second one? 43%. All right, and this one will be the SB121. This one will be the SB123. Fun, 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 yeah? Yes. If there was a third one, this equation's unapplicable. In which means it's officially outside of our scope for this class. Best answer. The best answer I can ever give y'all to a question like that is it's out of our scope, which means who cares for now. All right, Canvas will give you more practice. Let's move on to the other skill of the day. So, the mole concept. Lots of ways to apply moles. It sneaks into a bunch of different things that we do. But what is a mole? I want to remind you that this is a totally made up word that we came up with. Not we, I wasn't there, but that chemists came up with to talk about quantities of elements. So essentially, a mole is a square of an element on the table in regards to mass. So if I have 1 mole of carbon, if you round it, it has a mass of 12 because carbon is 12 for its mass. What if I have 2 moles of carbon? That would be a total of 24. Be 12 twice. What if I had half a mole of carbon? 6. Half of 12. So it's pretty straightforward. Now, when I say half a mole, we're not like splitting an atom in half. Because remember, it's a made up word. It's just an agreed upon way to talk about the amount of matter in front of you. So half of a mole of something is just theoretically half of what is present in the square on a table. I want us to focus on mole conversion since it's applicable in so many different areas of chemistry. But to do that, you have to know what things are equal to each other. The purple data at the bottom here will be given to you. You don't have to have that memorized. It states that 1 mole of anything equals its periodic table grams, which I just said. But secondly, 1 mole of something is Avogadro's number of molecules. 1 mole of anything contains 6.02 times 10 to the 23rd molecules.
Was there 2 twos?
I'm sorry?
Was there 2 twos?
It actually, and then it goes even beyond that. I'm just using the scale that's used on the AP formula chart. So, with that said, let's see if we can apply this idea to some conversions. Now you can see that I yellow highlighted the conversion factors up there so that you can glance easy. All right, the question asks, how many moles are there in 18 grams of sugar? How many moles in 18 grams of sugar? Now, dimensional analysis is the way to solve this stuff. If you had a bad experience, Eli, take that out of here. If you had a bad experience with dimensional analysis last year, like stuff like stoichiometry was your enemy, get rid of that negativity. We get to start fresh now. So just learn it from the beginning. I'm going to teach it from the beginning. So grip on. It's so repetitive. It's just a pattern. Learn the pattern. See the 18 grams of sugar? The given is always what starts the grid. So 18 grams of sugar. Let's assume glucose. What's the formula for glucose? Very good. C6H12O6. But it doesn't want grams. It wants to know how many moles is that. So we're going to draw a grid. All right, so what goes where? Well, what we're going to change into goes next door. So we don't want to be in grams. We want to change it to moles. So moles goes there. And then our special dimensional thing is the diagonal drag, right? Where we need something in this bottom square. So what is it? Well, you take whatever's there and you simply copy it there. Not the number, just the units. So I'm going to bring down grams of glucose. All right, so I did my diagonal drag. That will always match during this process. And then we set things equal to each other. It's the conversion factors, that yellow highlighter, the purple from the previous slide, that go in those squares. You just pick the numbers based on the units that you already wrote there. Like the top square, I wrote moles. So I look at that yellow highlighter, and the number next to moles is 1. The bottom square says grams. Look at the yellow highlighter next to grams is, it says periodic table. So grams is a bit annoying because you have to find a molar mass where you're adding up the parts. But it's an easy skill. Now, I helped you out here, so you don't have to get out of the periodic table. But I need the molar mass, the PT, of 6 C's, 12 H's, and 6 O's. And here's their masses in black right here. Carbon's 12.01, hydrogen 1.08, oxygen 16. So if you take that number 6 times, this number 12 times, and that number 6 times, it'll give you the PT grams of glucose. Beat me there. You should get 180.16. Run it again if you got a different answer. We all right? And then you solve. Multiply across the top, multiply across the bottom, divide the top by the bottom. Sig figs do apply here, so be careful. The sig figs never come from conversion factors, right? So the yellow highlighter stuff up there doesn't affect it. It's just that starting value, which was 3 sig figs. So I end with 3 sig figs. What you think? Let's do another one. Wait, what is funny? What is the laughing's kind of like spreading through the pot. Come tell my camera what's funny. How many molecules are in 50 grams of oxygen? So let's set up again. We start in the upper left-hand corner with the given. So we're going to have 50 grams of... How do I write oxygen? It's O2. Now, if you are not keen on that, here's Brinkelhoff up here. Those are the 7 elements that cannot exist alone. They're the 7 elements that if they try to, they drop a little deuce. All right? Which is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So you just have to know that those are your 7 elements that never exist alone. So there's the given. Let's convert. Remember, in the square next door is what you're changing into. We don't want grams, we want molecules. And then we do the diagonal drag, not the number. There it is. Yeah, yeah. All right, let's go fetch some numbers. Now we need conversion factors. For molecules, if you look at the yellow highlighter, it's Avogadro. If you look at grams, it's periodic table. So again, it's going to be 2 oxygens. Remember, I got you right here. There's 1 oxygen, so 2 oxygens is multiply across the top, divide by the bottom. If you don't remember how to get that symbol on your calculator, the scientific E, it's the second button and then the button above the 7. Again, to make the big E for times 10 show up, it's the second button followed by the button above the 7. Let's draw a card for this one. Get that answer. Let's go over to cluster number 2. Let's talk to seat number 3. Hey, 2-3, you knew it was going to happen. What'd you get? Anybody else get something slightly different? Did you get 0.41? So I don't know. You're so like it's weird to be wrong with that close. Um, yeah, I got 0.41. You must have just put a different digit. Maybe you added another 2 there. Um, anyway, yeah, I get this many molecules. Questions? So the sig figs, remember, are going to spawn directly back only to the given number, never the conversion factors. And there's 3 sig figs there, right? Both of those zeros are ending. We have a decimal present, so 3 sig figs to 3 sig figs. Now, I warned you when the lecture started that there was something at the end that was different than what you're used to, and that's where we are now. So refocus. Look here. Grams and moles cannot talk directly to atoms. This wasn't a big deal last year because we purposely, in honors, steer away from questions that it applies because we don't teach this angle. So listen to me say it again. Grams and moles cannot directly change into atoms. Only molecules can do that. So, if a question wants you to go to atoms, you first have to go to molecules. Now, you already wrote that down. It's on the slide before this. It's part of your notes. But let me demonstrate it for you. Look at this next problem. How many atoms are there? So it wants atoms. Are there in 2 moles of aluminum selenide, is what your slides say. It's going to start the same. So let's start with 2 moles of aluminum selenide. Careful there. Aluminum selenide is Al2 Se3. It's ionic. I checked the charges and I crisscrossed yesterday. The question wants atoms, but moles cannot go directly to atoms. Only molecules can. So what should we go to first? Yeah, molecules. And molecules can go to atoms. Right? This is not hard. It's just different. But the question doesn't just want atoms. Focus in on the question. It specifically says atoms of what? Atoms of aluminum. And that's usually what happens here, where you've got a compound, but it wants atoms of a part of the compound. And I'll show you how we're going to get there. Let's do our diagonal drags, though. That's all the same. So, diagonal drag, not the number. And diagonal drag. All right, here we go. Let's see if we can fill this in. Molecules and moles are both in the yellow highlighter. The molecules value is Avogadro. The moles value is 1. And here's where you have a new conversion factor. Overton, you are going somewhere. To attendance. Overton, attendance. Here's a new conversion factor. One molecule equals subscript atoms. One molecule equals subscript atoms. What does that mean? Well, look here. Look here. You're writing. I'll give you a second. One molecule equals subscript atoms. Look. One molecule equals subscript. What's the aluminum subscript here? Y'all, what that means is for every one of those formulas you have, there are 2 aluminums. Right? So we're on a different wavelength here versus the yellow highlighter. Because remember, the whole point of this is to set things equal to each other. And now we're ready to finish. So let's do this. Multiply across the top, multiply across the bottom, divide the top by the bottom. Yeah. Yeah, I just did. Yep. Down here?
Yep.
Because it's not molecules. So moles and molecules are 2 different entities. So yeah. There's right here.
Yeah.
Okay, because so at this point we're comparing molecules to atoms, which is not a part of this conversion scheme. It's a part of this conversion scheme, where it's always one molecule to the subscript atoms, which I know is a little foreign, but it's just another thing. The answer that I get is 2.41 E24. Yeah? My intention is to have you do the last one by yourself, but Flex has me sitting at only 6 minutes, so I'm just going to work it out. But interact with me. Stop me if I do something weird. But let's just look at one more problem. All right, unamas. Check it out. 654.5 grams. 654.5 grams of calcium acetate. That's a mean formula. I got you though. It is Ca, that's the calcium, then acetate is going to be in parentheses. It's going to be C2H3O2 from your polyatomic list. Calcium crosses a 2, acetate crosses a 1. We love nomenclature. Calcium acetate. How many atoms? Can we go from grams to atoms? No. Only molecules goes to atoms. So let's go grams to molecules, and then molecules to atoms. Atoms of what? Look closely. What's the question say? Atoms of calcium. That's important because it's pinpointing a part of the formula. Drag your diagonals. Stop me if anything is funny. Here we go. Molecules in grams. That conversion factor is in the yellow highlighter. For molecules, it's Avogadro. For grams, it's periodic table. So that would take us a second. I've already got the number for you. But it's 1 calcium, 4 carbons, 6 hydrogens, 4 oxygens. If you added it up, you'll get 158.17. Molar mass of calcium acetate. What number goes here? It's going to be a 1. Because look, we know it's a 1 here. Here's our new thing. 1 molecule equals the subscript atoms. What's the subscript of calcium? It's 1. So even if you'd forgotten to do it on this one, it wouldn't have changed your answer. But what if it had asked for hydrogen? What's the subscript? What was the total amount of hydrogens? Yeah, it would have been 6. But anyway, I get a final answer as we're in our 2 minutes. You should verify. I hope you're clicking along, but just see if you match me. Watch your sig figs.